Hello, physical science. Today's lesson is on waves. Today we're going to be looking for about 10 minutes of note time. Just so you know, any kind of underlined words or phrases on my PowerPoint slide means that you probably need to write something down. Plus, be sure and take extra notes or write down questions on the side that you can ask whenever we see each other again. So, for getting started, let's first talk about what a wave is. And I don't just mean water waves or sound waves, I mean all kinds of waves. What do all waves have in common? A wave, no matter what kind we're talking about, is nothing more than a disturbance in matter moving from one location to another. So we're going to talk about what a disturbance is and also what matter is. A disturbance is just moving something from where it shouldn't be or where it normally wouldn't be. And so, like if you take a string and you pull it down, it might snap back up to its resting position. And that's all a wave is. And it's something that has to move. So there's the disturbance, and then that disturbance moves. So we have a movement of some material away from where it would normally be, and it's called the resting position. So to the left of this wave, if you look at the picture below, the left of the wave is a resting position, and behind the wave, to the far right of that picture, would also be resting position. And this is the lowest energy state. Water is going to be pulled down by gravity, and it's going to find the lowest spot in its container. In this case, it's a wave pool. But a disturbance, a large amount of energy, caused a disturbance in the water at the beginning of the wave pool. And then this wave traveled through the water, carrying the energy with it. Where we see the actual disturbance is at the peak of that wave, and that's at the tallest part is where it's at its highest energy. Waves, I have to say, they move in predictable ways, which helps us to understand how waves affect everyday life. It's important to understand how waves work. You're listening to me right now because of Wi-Fi waves. These are radio waves. We see because of light waves. Waves in the ocean kill many, many people. So understanding how tsunamis travel is really important. Earthquakes, waves are traveled through the Earth's crust. So many waves. Important that we know all about waves and how they work. As a big reminder, it took energy to create that initial wave in the water. So to disrupt the water required energy, and then that energy is still in the wave. You can feel that energy if that wave hits you if you're in the wave pool. That means that all waves is something that carry the energy of the original disruption. That's what it is. Now names, we can name them. You've heard me talk about waves already. Waves are named according to the matter that they disrupt. For example, water waves. They disrupt water. No surprise there. Sound waves, you may be surprised, they actually disrupt air. So right now, I have pressure waves that is disrupting the air molecules that are making its way up to the speaker, and that's how you can actually hear me. It's the same thing that affects our eardrums. The pressure waves vibrate our ears. That's also one of the reasons why sound does not travel in outer space. There's a vacuum, and there's no air to disrupt, therefore there is no sound in outer space. Seismic waves you've learned about in junior high school and then later on in elementary school, they disrupt the Earth's crust, and they transfer huge amounts of energy from the epicenter of the earthquake all throughout through the surrounding areas. And the final type of waves that we're going to be looking at are things called electromagnetic waves. And these are a little bit more difficult to understand because they actually don't disrupt matter. They disrupt a balance of forces. And the two forces we're talking about are the electrical forces and the magnetic forces. Normally, those forces are balanced in the air around us and in really plastic and the walls and everything. They're balanced because they're not moving around. But the electromagnetic waves, they are actually a disruption in that balance that moves through materials. And that's how I'm talking to you right now, through electromagnetic waves. More on that, there's a whole new section just devoted to electromagnetic waves. Of those 4 different kinds of waves that I just named, they can all be categorized into 2 different types, and they're called transverse waves and longitudinal waves. And let's play a video just to show you the difference between them, then we'll come back and talk about it. Longitudinal waves. The disturbance is moving in the same direction as the energy is moving. So energy is moving from left to right, energy was moving from left to right, and the disturbance was moving from left to right. That's a longitudinal wave. Now here comes a transverse wave. The disturbance is now moving up and down this way, but the wave of energy is moving that way. And if you think about it, the disturbance up and down right here, it kind of makes a letter T if you get really creative, and that forms a transverse wave. So let's watch a transverse wave. There you have it, nothing fancy about it. Pause here. All waves that we're going to be dealing with, like we said, divided into two types of waves. And longitudinal waves and transverse waves. Sorry, brain fart. We're just going to keep on going. During a longitudinal wave, this is the first type of wave that we talked about. The disruption of these particles is moving in the same direction as the energy is flowing. So in the picture down below, you have the slinky and a hand is hitting the slinky. And that is going to send a wave through the slinky from the left to the right. So if it's traveling in the same way, longitudinal waves. Here's an example of some other longitudinal waves that you're very familiar with, are sound waves. Sound waves are sometimes called compression waves because what happens is a speaker, in this case, is actually hitting the air. And when it hits the air, it's going to make a little compressed spot of air where there are little high pressure waves, and then those high pressure waves move throughout the air. And they travel to your ears, and then you can actually hear because of that. Those are called longitudinal waves. The second type of waves are called transverse waves. So by shaking a rope up and down and seeing the wave move through the rope, or actually seeing water move or waves move through water, that is going to be a transverse wave, where you have an up and down motion, but still the wave moves. Water and seismic waves, they do move like this, and also the electromagnetic waves, or light, they move like this. The picture shown right there is a good example of water and how water is actually moved, or seismic waves and how seismic waves move. That is not a good way of thinking about electromagnetic waves, because remember we said that electromagnetic waves, they don't move particles. They only move unbalance the forces, the electric force and the magnetic force. Parts of a wave are important when we start looking, because we're going to be building this really cool wave machine tomorrow, just so you know. That involves duct tape, gummy bears, and shish kebab sticks. So it's going to be really neat. It's going to stretch from one side of the room to the other. So get excited about it. But before we go on to there, we actually need to know some terminology. So here come the terms. And this is a transverse wave you're looking at. If you notice, we have up and down motion, and then it is moving from left to right. So the first thing you need to know is the crest. All right, the crest is the highest point on a wave, and it's the farthest away from the rest position. That rest position is the lowest energy state. Opposite of a crest is something called a trough. And a trough is just as strong as a crest. It's just in the opposite direction. So the farthest parts from the resting position, we can call it the crest, and we call it the trough. The amplitude is the distance between the resting position and the crest, or the resting position and the trough. And then finally, the wavelength is the distance between either two crests or two troughs. We're going to be looking at how each of these variables can affect the speed at which the wave travels, which is important to know. All right, I think that's all I have for you. So if you have any questions, make sure you write those down. There is going to be a homework sheet that's coming along with this. So refer back to the video or to the notes to help you out with that vocabulary sheet. And we'll see you soon. Bye-bye.